Okay, super. Our next speaker is Thomas Bland from Innsbruck.
Cool. Thanks, Richard. Right. Good morning, everybody. Yes, I echo Julio's. I echo Julio's thoughts of for being here when you could be seeing Nobel Prize winners. I don't know what I did to deserve this, but fine. I'm going to tell you about some of our recent work in Innsbruck. I'm a theorist, so I'm going to be here maybe presenting a lot of experimental data. Don't blame me if I get some of the experimental details wrong, I'm afraid. And it really echoes and follows on from exactly what Julio was saying, which is excellent. Apologies to the people who just come into the room. I will try and re-explain everything. So there are a lot of interest in these long-range interactions, and so this is a long-range interaction session. And so over on the left here, we have the lanthanides, these magnetic atoms that I'll be talking about today. And obviously, this conference is there's a lot of information on the new BEC of molecules, which have a lot stronger dipoles in the Debye range, and Rydberg atoms, which go even further beyond. And obviously, there's other systems that really rely on some of the physics from long-range interactions. So actually, there's a lot of stuff we'll talk about today, maybe even be relevant to other systems with these long-range, perhaps anisotropic interactions. So lanthanides, like I say, there's now a lot of experimental groups with the erbium and dysprosium. There's now a few other lanthanides joining in the fun. And why are they special? Well, for the ultra-cold atom case, immediately you can see that a lot of really interesting physics comes out from just the balance of two different types of mean field interaction. So we have the celebrated, well-understood, this contact interaction at very low energies, just billiard ball-like smashing of atoms, and its long-range anisotropic interaction given by this sort of term here. And we can sort of describe this balance by this interaction parameter epsilon dd, which is the ratio of the coefficients of these two interactions. And to access this supersolid regime, this exists in this dipolar-dominated regime. But actually, in this regime, our scales break, and we lose everything to the right. But lo and behold, nature had a little plan for us and gave us these beyond mean field effects, this extra repulsive interaction sort of, this repulsive effect which scales with the density at a higher order than the interactions. So as this system wants to collapse because of the dipolar interactions, we're saved by this beyond mean field effect. That's basically all I'll say about this, but just keep it in mind that this thing is here. So what are some special properties of these dipolar gases? Well, the anisotropic interactions give rise to an anisotropic density profile, even in the absence, in a cylindrically symmetric trap, for example. So if I tilt my B field into a pancake-shaped trap, then my atoms want to align along this B field, and they get this magnetostriction, this stretching effect due to the atoms. The excitation spectrum has this famous Roton minimum, and this is down to, as long as you have some confinement, now you have this magnetostriction, but this hits a wall, and so the next atom comes along and wants to leave a bit of a gap for its now side-by-side neighbor, and so there are some waves which have lower energy configuration, a particular finite wavelength, and this is this Roton. And this was observed in experiments, so you can do Bragg spectroscopy at very large scattering lengths where we have comparably smaller dipolar effects. This you have at low K, you have one as linear spectrum, as phonon-like spectrum. But as you start to lower and lower and lower the scattering length, you can bring down this Roton minimum. And eventually you can touch zero, which is obviously the interesting regime we'll be discussing today. And also you have droplets. So now, unlike, for example, bright solitons that exist as a balance between the mean field attraction and the kinetic dispersive energy, droplets are self-bound solutions in 3D that exist as a balance between the slightly attractive mean field and this repulsive beyond mean field effects. And we need all of these ingredients to describe what a supersolid is. So if I take some dipolar atoms, say just in free space, what do they want to do? Well, magnetostriction first tells us they want to align themselves head to tail. Then we add in some interactions, and this tells us that we want a liquid droplet of the self-bound anisotropic solution. And if we add in confinement, well, this then tells us that we want to have some preferred separation, this roton kind of effect. And if we carefully tune our scattering length, we can do in the experiments fresh back resonances, we can get the wave functions just to overlap with each other. And now we have a continuous single wave function, one global phase coherence, and density modulation simultaneously. And this is sort of the cartoon version of what a supersolid is. Okay, so as Julia's already nicely explained, this was first seen in the dipolar gas back in 2019, simultaneously from 3 groups from Modugno, Fau, and Faleno. And the initial observations were sort of this one-dimensional change, so we're sort of looking above the droplets for these pictures. And then in the last few years, we've changed the aspect ratio, improvements of atom number, we'll be able to see this 2-dimensional supersolid formation. And it's just a list of some nice properties, but you can see that if you quench the scattering length, go from, you tip your scale from less dipolar to more dipolar, you induce this density modulation. Okay, so there's been a lot of talk about, well, what gives you the super part of a dipolar supersolid, right? So what do we want? Well, we have 2 broken symmetries, so we need 2 Goldstone modes. And so some of the first experiments after 2019 were looking for the fact that you have 2 branches in the excitation spectrum and and 2 Goldstone-like responses in this finite size system, which is maybe a bit counterintuitive. And then, of course, we've had the really nice results just shown to us now, where we're measuring the superfluid fraction, which is obviously, this is not 0, that we have our super part. And also, as Julia's mentioned, that the scissors mode, so some response to rotation, is a bit ambiguous in these systems. As it turns out to be some multi-mode response to any perturbation, and it's really difficult, at least from just the case of rotating a harmonic trap and back again and seeing the dynamics. It's very difficult to extract what about this rotation is superfluid. And so I think there are still prospects in the future. I know Stringari had some nice proposal to how to still extract the superfluid part from a scissors mode excitation, but for now that's not the case. But what would be the case, well, would be rotating the gas and seeing vortices. Quantum vortices, the hallmark of superfluidities, is something which we would like to see, and we should be able to see them by rotating a supersolid. Okay, so how do you rotate a supersolid? Well, in the labs, we chose a particular method. First, we're talking about what do we expect to see? Well, okay, if we rotate a bucket of any fluid, then, okay, normal fluid, we should just see this kind of response. But a superfluid special because it does nothing, but it's only true for very small rotation frequencies. And we rotate fast, we get lots of tiny identical vortices. And if we look at these guys, then they have 2 pi winding in a phase. So we require this global phase coherence, and there's a density hole in the center. So these are the things that we're looking about. But what about vortices in a supersolid? Well, we use this method called magnetostirring. This is what actually Francesca named this when we were looking at this. But the basic idea is very simple. If I have a non-dipolar gas, maybe I turn on my dipolar interactions, what do I get? Well, I get magnetostriction. And I have a cylindrically symmetric trap in this sort of density projection. And if I tilt my magnetic field, I break the cylindrical symmetry. And now if I can rotate this, then I can impart angular momentum. And this is what the kind of theory said. And this is all done in the lab with some compensation cage for the homogeneous field, just to start to have some angle and start to rotate this homogeneous field. This is the magnetostirring, so it has some potential analogs with classical ferrofluids, right? And you can maybe even start to see where this is going. And if I rotate the field, then my ferrofluid follows the magnetic field rotation. This is quite cool. Okay, so what do you do if you, what do you see, if you do this in extended Gross-Patevsky equation? So this GPE includes the effects of this beyond mean field term, the dipole interactions, etc. And so we rotate and we see this expected elongation of the cloud. This is like angular momentum in a superfluid without vortices. And at longer times, eventually this breaks down, vortices penetrate the condensate surface and come into the center. So this is like, these are the maybe the first predictions are dipolar vortices, and use this magnetostriction effect. And let's do it in an experiment. Well, so this top row here is taking experimental parameters available and running the theory again, and then these are some experimental images after a very short time of flight to make the vortex core ever so slightly larger. And yeah, so we were able to observe that there's a breakdown of this of the pure superfluidity, and then we can bring in these quantum vortices. Okay, so it'd be nice to have something that's unique to dipolar physics. So actually, in a dipolar gas, a very strong dipolar gas, the vortex lattice is also anisotropic. So the vortices behave like little dipoles. They want to align along the B field, and so you get this stripe lattice effect. And actually, in experiment, we were able to see this. So you can see them in the residuals. We're able to see peaks in the density, and you can start to see that after long times, you get ordering of the vortices into this striped lattice solution. Okay, this is all BC. I'm here to talk to you about supersolids. So the first question is, well, does magnetostirring work for supersolids? And if I tilt my B field, then I can see from the experimental images down here that my droplets do follow the magnetic field. This is like a projection of the 2D density. It's also interesting because if you tilt the B field all the way, you no longer get, let's say, these droplets. You might get like a stripe solution when looking above. So it's good to see that you can still count 4 droplets, let's say, when we tilt this magnetic field. And then to see what happens when we start to rotate the B field. Well, we can see the droplets follow the magnetic field. And actually, this particular experiment was the time from here to here is about 250 milliseconds, and we're still able to count the droplets. And this is really important because, as Julius mentioned at the end there, we have 3 body losses. There's such high densities in the supersolid state that the lifetime can be quite limited. And so actually, and we always have this idea, it's quite a fragile state. So the fact that they can live long enough for us to do some rotation, perhaps count some vortices, is excellent. So again, let's go back to our friend, the Grozovsky equation. The top left here is showing the projected density. The bottom left is showing the phase, where you'll see some 2 pi windings at some point. And then this is just some density isosurfaces of rotation. And around the 600 millisecond mark, you can see the vortex enters the center of the state, and it's marked here by a black line, just a peak in the kinetic energy. It's all this isosurfaces. And so we can see that this magneto-stirring effect does bring in vortices. And here, this is as I'll show you in a second, this is a very slow rotation frequency relative to the trap frequency. And this is important because in non-dipolar gases, in non-supersolids, in normal superfluids, it's quite well known that you don't generate vortices from this kind of rotation until you hit a resonance with some quadrupole mode. And so actually at low frequencies, we see almost no response to an elongation. And at large frequencies, we see lots of vortices. And in a supersolid, we find it is at lower frequencies, we start to nucleate vortices. And we can look at the vortex number as a function of omega here. For the BC case, you get this resonance-like feature up here. And a supersolid case shows a lot of vortices with an interesting feature down here, which I'll explain in a second. But crucially, there's a window where only the supersolid state can produce vortices. So let's deconstruct this a little bit. So as I mentioned, this here is a resonance feature with the quadrupole mode of the superfluid. So as Julia has just shown us, there's a reduced superfluid fraction. So the quadrupole, the superfluid quadrupole mode of a supersolid is lower energy. And so this same resonance feature just moves to the left. And this is around the superfluid quadrupole mode. And there's also more quadrupole modes because we have more broken symmetries. So there's also a crystal quadrupole mode. And actually, the behavior around this one's very different. It's more like a threshold response you'd expect from some rigid body rotation. And so if we rotate faster than this, we're just able to freely nucleate more and more vortices. And so this is kind of the explanation of this diagram. Okay, so there is an issue. How do you see holes in a density in zero density? This was somewhat suggested by, or solved by Stringari and co. So if you rotate a supersolid, you gain a vortex in the center, and then you quench the scattering length back into the BC phase. You lose the density modulation, but you create the hole. And this vortex survives this quench. And this is quite reminiscent of measuring superfluidity in the BCS-BC crossover, where they ramped from the BCS to the BC phase before taking the image and implied the evidence of superfluidity from the resulting density image. Okay, so does it work? Well, in our case, so this is now GPE again, but for the experimental parameters. So in the BC case, it's quite simple. We can just count our vortices. In the supersolid case, we do some rotation, and then we quench the scattering length, and now our vortices exist, and we can see them in the density, and we hope this will apply to the experiment. So here's our initial states. On the left, I'll show BC cases. On the right, I'll show initially supersolid that quenched the BC cases. And you can see at low frequencies, we see just a normal Thomas Fermi-like cloud. At very large frequencies, there's a turbulent-like cloud after about a second of rotation. And in this little Goldilocks zone here, we see only vortices if we were initially in the supersolid phase, rotating at frequencies that shouldn't nucleate vortices from the BC. This is some, like, as I labeled up here, like an indirect measurement of the impacted vortices. And let's repeat this over lots of rotation frequencies and time, and we can see there's this resonance-like feature appears at large frequencies, which also we see in experimental images. And in a supersolid, so there's this expected double sort of method where we see the crystal-like response and the superfluid-like response. We certainly see the crystal-like response from experimental images. And there's some weak evidence. When you integrate over time, you can see there is a little peak around this case. But actually, when we compare a bit deeper into the theory, I think if we add a lot of temperature to our state, this really obfuscates this little feature here. And so maybe this is an explanation for why it's harder to see in the experiment. Okay, but certainly there are two very different responses due to this crystallization. So what about the direct method? If we do some time of flight analysis, what do we see? Well, so if we don't have a vortex, this is the GPE again, and we just turn off the trap from our taking experimental parameters, what do we see? Well, we start to see this interference pattern. But actually, the droplets themselves are very self-bound, right? I mean, they're self-bound, so they want to sit together. Tilman-Farrell's got around this before from interference measurements by quickly quenching the scattering length to very large values, and then doing a time of flight, and you get this explosion of the density. But here, actually, it turns out to be quite nice, this feature, because when you compare to the case when you have a vortex, you still have the zero density, but now rather than seeing this triangle or this filled triangle, you see a hole of a triangle. This is around 36 milliseconds time of flight. So again, let's start to rotate in the experiment. What do we expect to see? And then this is what we do see. So when we rotate very slowly or at zero frequency, we see this kind of interference pattern with this nice filled triangle. And when we rotate a lot faster, we start to see this solution appearing more and more, telling us this is the vortex that's in the center. Okay, so I want to show you some new stuff. So I like to guide your eye to the big preliminary in the top right, and if you're not clear, it's there. And so if you were very, very astute when you were watching the video before, you may have noticed this already, but if you follow this point I've put here for the video, what you'll see is that when we kick this rotation frequency, is that the droplet starts to rotate around its own axis. As time continues, everything suddenly becomes quite rigid, and suddenly all three droplets start to rotate together. It's this transition from this sort of multi-frequency response with the droplet, and you can see this from just plotting the trajectory of this droplet. There's a sort of a double rotation, double spiral, and then one very large spiral. And actually, this exactly coincides with the time when a vortex goes into the center of the cloud. And this is the quantum, this makes sense. It's carrier of angular momentum, so it's kicking almost the droplets around. So we can describe this by taking some guiding center and cyclotron coordinates for our droplet. So center of mass being the guiding center, and this sort of cyclotron being the coordinate at the top of the droplet. Again, this is the theory for now. And we can decompose this between the guiding center and the cyclotron, and then we can plot those two values. And here I mark, this is exactly where, from the theory, the vortex gets to the center. And if we plot these two values, we see that the cyclotron always follows exactly the driving frequency of our rotation. Whereas the guiding center is something that catches up, but only catches up when a vortex enters the cloud. And so being able to just measure the center of mass of each droplet in the experiment, for example, would be a clear indication of when a single vortex enters the system. And so here's again some theory. You can start to see that there's no synchronization over here, but then everything in the lab frame becomes quite straight lines at some later time. And here's some experimental data. And so here you just plot a circle for every detected position of a droplet for many, many different experimental runs. And if you're struggling to see, then the guide to the eye does see that actually there is the kind of appearance of these straight lines. And here we've just added, this is actually at 2 pi over omega. So you pick the first one based on your favorite line, and then the rest will follow along later. Right? So this is one thing, but I also think it's quite nice to show. It would be nice to show when a single vortex comes in very clearly. And one way of doing this is slowly ramping up omega. And so here, again, now we're in theory able to label each droplet, and we're plotting this in a rotating frame. And then here is the point when a vortex enters the system. And then we do this again for the experiment. Okay, apologies, the y-axis is flipped between the two. But again, in the rotating frame, you really see that everything is very slow frequencies, everything's nice and synchronized. There's a sort of a desynchronization when our vortex enters, and then everything resynchronizes again. Okay, so this is very nice. I would like to talk very briefly about what can we actually do with these vortices. So neutron stars is the obvious answer. I knew you were about to say it. So they're much bigger than dipolar supersolids in all senses, but they have this enormous mass, and they have this really tiny, tiny radius, and they have this enormous density. And then there's a lot of predictions that show they can also show these superfluid properties. Maybe we always think about this dipolar supersolid being a case where you lower the temperature to increase your de Broglie wavelength. And now you have overlaps of these wavelengths, and you have this macroscopic sort of giant atom idea of a superfluid. Here we just take a lot of atoms, we just push them really close to each other, and now their little wave functions are overlapped just from density alone. And neutron stars, some of them are pulsars, and we can observe from Earth this pulse as the magnetic field happens to point at Earth. But there's an emphasis over time, because of this electromagnetic radiation emission, they're slowing down. But every so often we observe a glitch where they speed up and then eventually slow down again. And the explanation of this is an expulsion of quantum vortices from the superfluid core entering the solid crust, which is the actual thing we observe. This is a glitch, and the explanation of this is superfluidity. So this is kind of some picture of the structure of a core of a neutron star. Really, this should probably have a big question mark in it, because there's lots of competing theories about what's really in the center. But also out here, we know it goes from something superfluid, liquid, to something crystalline, and in the middle, there's a coexistence of both. There's a coexistence of the solid part and the superfluid part. Starting to see maybe where I'm going with this. And so we can label this as a supersolid. And we took our dipolar supersolid and we rotated it, and we saw that if you slow down the external rotation, actually you can engineer this glitch-like phenomena in a dipolar supersolid. And so here this is, like I say, heavily engineered. What we're doing actually is we're looking at when the vortices leave, and we are speeding up the trap as if this is the solid crust on the outside as a vortex leaves. So we're taking this angular momentum and giving it back to the rotating trap. But actually, I think it'd be a really interesting experiment to just simply observe vortices leaving this crystal structure, because this should maybe be able to tell you how do vortices move through these sort of pinning sites in a loose crystal, a crystal with excitations. This was something like the the neutron star supersolid. Okay, so very brief summary. I've talked to you about the superfluidity of dipolar gases in both the superfluid and supersolid states, and some nice new results on this idea of synchronization between the superfluid and the solid part. And I'll just leave you with some things we'd like to do next. So I've maybe answered some questions how superfluid is a dipolar supersolid, but it'd be nice to ask the question how solid is a dipolar supersolid. So this was a nice talk given by Pramod yesterday. What we were doing here is perhaps perturbing our supersolid in one direction and looking at, the video is not a video. Let me show. Is this just going to play? Fine, I'll play here. And we can see that if we kick this way, then there's a propagation of a wave, a shear wave transversally, and this is only something that's possible in a supersolid. So we're hoping to be able to relate this to like a shear modulus and make the helium people happy. Okay, so let me end by thanking everybody who works in Innsbruck. The highlighted people are those that worked on the on this experiment and the theory for the results I've shown. Thanks.